All right, here we have a frame analysis problem, and as we already know, when we analyze a beam, it has the capability to undergo bending, okay, and it can also undergo rotation. But when we say frame has the capability to undergo bending, rotation, and it can also has the capability to undergo translation as well, along with the capability of twisting. So when we do we have a frame analysis problem in which we have basically two sections, which are rectangular, basically overhang beam frame placed over here, and on it the load applied is a pressure loading as 800 pounds per feet. Okay, the vertical length of this frame from the origin, if we assume this as the origin, is 9 feet, and from here the horizontal length of this frame is 10 feet. Okay, so they say we have to solve this problem on Ansys. Okay, so the solution will be slightly different when you are analyzing a beam. So, okay, so the material selected for this frame is 30 into 10 to the power 6 pounds per inch square. It means it's a steel beam. The Poisson's ratio will be 0.3, as you already know it. Okay, so we have to analyze it, and they have given you the depth of this basically the vertical depth of the section of this frame is 12.22 inch. The frame is fixed on the at this point, and it is also fixed at this point, and we are interested in calculating the deflections and the rotations of the frame under the given distributed load. Okay, so here we will take an assumption, and we will assume that this frame is basically the section of this frame is an I section beam, and we assume that its designation could be given as W12 into 26. You can assume any respective sections. Here we are assuming it W12 into 26 based on the data given to us, as the depth is 12.22 inch. The area is 7.65 inch square, and I is 204 inch 4. So the closest of the designation beam that we can select is W12 into 26. Okay, so this is very important. Okay, so if we go over here in the I section beam, as we have assumed an I section beam, so W12 into 26, the area is 7.65, the depth of the beam is 12.22 inch, the thickness of this web. Okay, so this is the web, and this is its thickness is TW, which is 0.23 inch. The flange width, this is the flange width BY, this is also the flange, is 6.490 inch, and again the thickness of this flange, TF, this both are flanges, is given to us as 0.380 inch, and the second moment of area about this x-axis is 204 inch 4. Okay, so these are the values of interest when we are solving the frame analysis. So I will be putting these values when we are solving the problem. Okay, so we can now start with all this input data, which I've already told you will be inputting it while we're solving the problem. Okay, so let's start and do it. This is the structural problem. So this is over here the preprocessor. So the element selected is going to be for us is beam. We say 2 node 188. We can also select 3 node, but computationally it will be more cumbersome. So we over here it, in order for convergence to be better, we can make it we can say quadratic. You can also take cubic also. It is up to you. So this is done. Now we will go to the material properties, as it is a steel. So we will say structural, linear, elastic, isotropic, and we will, as given to us, we will say 30 E6, and the Poisson's ratio, as it is steel, it's 0.3, and this 30 E6 is in English units. Okay, because it is given in pounds. Okay, and we and basically as dimensions are given in feet, we'll convert it into inches. You must always remember this. It's very simple. Okay, so now we go to the sections, and the section selected is basically an I section. So we can very easily consider this as the I. This is our I section, and again just remember this is the flange width W1, W2. This is the thickness of the flange T1. This is the thickness of the web T3. T1 and T2 are same. W1 and W2 are same. Okay. W3 will be different. Okay. So based on the dimensions given to us over here, these dimensions, we'll be inputting it very carefully. So we know what is W1. W1 is basically again the width of the flange, which is 6.49. W2 is also 6.49. W3 is given as the depth, and the depth is basically 12.22. 12.22. What is T1? T1 and T2 are the thicknesses of the flange. So the thicknesses of the flange are 0.380. Okay, and T2 will also be 0.380. And what will be the T3? It is the web thickness, and the web thickness is given as, from the data we can say it is 0.230. Okay, so remember this is 6.49, 6.49. This is the flange width. W1, W2, W3 is the web height. W3 is the height of the web including the flange total. So it is 0.380. Sorry, it is 12.22. The thickness T1. This is T1 and T2 are the thicknesses of the flange flanges, is 0.380, which is inches, and the thickness of the web is 0.230 inch, and you can basically apply it, and you can preview it also. This is the dimensions that we have gotten over here. This is the area as given to us in the question. So this is our area, the second moment of area. Okay, so these are we've got it, and again you can also make it mesh it also if you want to mesh as of the section as 4s are fine. So we can say it as 3. You can have limit of very fine as 5, just to save computational time. We can make it 3. Okay, and we can review it and we can mesh it. So now it has been meshed, and these are the dimensions that we have taken. Okay, so I hope you understand this. And we'll say it okay. So plot, replot, and what we do now is basically we need to model it. Okay, so when we say modeling, so we will be showing create nodes. Okay, so in order to continue, we must first see the dimensions of our frame, and if you look at the dimensions, this is will the first point. This is our origin 0, 0. The height will be is 9 feet. So this second point will be on the x-axis. It will be 0. On the y-axis, 9 feet into 12 will be give you 108. So it will be 0, 108, and this point, if this is the origin, will go in the negative axis. So this will be since this is 10 feet, so x-axis will be 120 inches, and the height will again be 108. But since this 120 inches is going on the negative x, it will be minus 120, and the height is constant, which is 108. So these dimensions will be inputting. So you must remember this. So we will say in active coordinate system. So this will be our first point. Will be again. You can say it will be 0, and again it will be 0, and we can apply it. Our second point on the x will be 0, but on the height it will be 108. We can apply this. The third point will be, the height is constant, but it's going to be minus 120. And here it is. We have got the point 1, point 2, point 3. Okay. So now this is done. Now we can basically create nodes. Have been done. We can basically create, out of these nodes we can create elements. Okay, so we can say these auto numbered elements through the nodes, and we have the nodes node 1 to 2 we can apply, and then the second node 2 to node 3 we can apply this, and it is okay. So now this is being done. This is from 0 to the vertical depth is, this is 9 feet and this is 10 feet. Okay, just remember this. Now once this is being done, now we have to apply the boundary conditions. Okay, so when we apply the boundary conditions, okay, we have to apply it as loads. So we will apply loads, and you remember, if you remember this, it is fixed here and it is fixed here. So apply structural displacement. The endpoints of 1 and 3 are basically nodes. So we will say on nodes. One is this one and the other one is this. And since it is fixed support, we'll say all DOF. And we can basically constrain it also. And this is being done. Okay, so this is being done. Now we have to apply the forces or the pressure. Okay, so how to apply the pressure? If you look at it, the picture, this is the pressure, 800 pounds per feet. Okay, so we wanted it to be in, everything is in inches. So we will say 800 divided by 12 will give you 66.66 pounds per inch. Okay, this will be treated as the pressure. So the pressure when applied, we'll say pressure, and this pressure is basically on the beams. Okay, so we will say it here, click it, and we'll apply. Okay, the load key, since we need to apply the pressure along the negative y, along the y-axis. So it is when we apply pressure along the x-axis, it is 1. When we apply on the y-axis, we'll make it 2. And since the pressure is along the negative y, so we will write it as minus 66.67 pounds per inch. This is the pressure, and we can apply it very safely over here, and you can see the pressure has been applied. Okay, so once this pressure has been applied, where the boundary conditions has been applied, the loading has been applied, so it is all set now. So we can basically ask Ansys to solve it. So solve the load steps. Let's see. So this has been done. Again, the problem dimensionality is 3D. Its displacement is being given. Analysis types, it's basically rotation 1, 2, 3, 4, 5, 6. All these capabilities are there in this element of ours. So plot, replot. Okay, you can say plot the elements is being there for us. Now once this is being done, let's see how the output is being shown for deformation. Plot results, we said deform plus undeformed. Okay, so this is the deformation has been generated by Ansys. Okay, so you can just make it more clear if you want. You can go for the ISO. Okay, this is the ISO. This is the front. Okay, you can basically make it about. This is the front view. Okay, this is the because the pressure is applied, so it is fixed here. It is not fixed over here, so maximum bending has been coming over here. Okay, so and we can also go for the contour plot, and we'll say the nodal solutions. As he has asked in the question to us, what has he asked? Deflections and rotations. Okay, so displacement vector sum. So again, the displacement generated is 0.0017 of an inch. Okay, this is the displacement maximum over here. And what about the rotation? So rotation comes out to be 0.002196. Okay, this is the value of the rotation, 0.002196. And as we have done it this, he has asked you, but still we can take further more outputs from Ansys. Is basically we can calculate the bending stresses, because you know as the force is applied, pressure is applied over here, it is going to bend. Okay, so along that we can say that this will have the bending stresses, as it is a section, it will have bending stresses at the top and it will have bending stresses at the bottom, and it will also because it has the capability to undergo axial deformation, will be also axial stresses as well. Okay, so we can, if we want, we are not being asked, but we can basically do that. We can construct an element table out of it if you want, and we will say, okay, the element table, again we can say the element table for uh, uh, beam bending stresses along the y-axis. We can say stresses along the y-axis of the beam top. Okay, we can say this. So it will be basically 32, comma 37. One of this we can apply. The other one we can also go for SMIC. It will be again SY for the beam, but it will be for the bottom. And for this, the element pole symbols will be numerical symbols for element pole is 33, comma 38. We can apply this like this, and once for the axial stress, for the axial stress, axial stress, the Paul symbols for the Paul numerical symbols for will be 31, comma 36. Okay, so we can say okay for this, and we can close it. And once it is being done, you can again say plot results, and you can basically list results, element solutions. Here it is, S by BT, S by BP. This, if you want. All right, these are our results that have come over here for us. If you look at it, this is 3879 for the S by BT. It is 3879, and this is 7146. And for the S by BP, it is minus 3879 and minus 7146. The axial stresses for the element 1 is minus 465, and for the element 2 it is minus 76.537. Okay, so this is how we calculate them. You can also basically get the reactions that is being generated. If you want, the reactions generated is this. If you look along the fx, there is no axial bending, so they have been cancelled down. This is the fy, very important. At node 1 it is 3522, and at node 3, the third one, it is showing as 4477.6. okay, so again this is pounds, remember, and the bending moment will be in pounds, inches, because it will be along the z-axis, the forces along the y. So it is 0.11984 e to the power 6. So this is how we basically solve a frame problem in Ansys. I hope you will be able to understand it, and as always, take care of yourself, because you are worth it. Thank you very much, and you have a wonderful day.